So as we're starting this stoichiometry using gases, I wanted to go over kind of a roadmap that we've seen before. So this first line going across in green, we first started talking about grams going to moles. Moles of A is related to moles of B by the molar ratio, which is the coefficients of the balanced equation. So those balanced equations are balanced in terms of moles. So if you have solids, you're going to have to convert grams to moles using molar mass, and then convert to moles of your other substance, and then use molar mass again to get to grams. So that's where we started. And then when we were talking about solutions and titrations and things like that, then you might have a solution of A and a solution of B, and the relationship between liters of solution of A and moles of A is the molarity. So remember, molarity is moles per liter. So if you have a solution, you're going to use a molarity to do this transformation, not the molar mass. And then you would do that transformation from moles of B to liters of B with the molarity concentration. For gases, the liters of gas, which would be the volume, and the moles of the gas, which would be N, the number of moles, those are related with the ideal gas law. So you can use PV equals nRT to find the relationship between the liters of gas that you have and the moles of gas that you have. If you are at STP, standard temperature and pressure, then 1 mole of gas would be 22.4 liters. So that would be the relationship between the number of moles and the volume if you are at STP. And so one of those two equations can be used to convert between moles of substance and liters of substance if it is a gas. So let's go ahead and use that type of roadmap in stoichiometry problems with gases. So we want to know the volume of carbon dioxide gas, and we are starting with the mass of sodium bicarbonate. All right, the relationship between carbon dioxide and sodium bicarbonate is given by the coefficients in this equation. It's a 1-to-1 molar relationship. So starting with grams of sodium bicarbonate, we are going to need to get to moles of sodium bicarbonate. And then that can get us to moles of carbon dioxide gas. And then once we have the moles, that is N. To get to the liters, or the volume, we're going to need to use some gas laws for that. So this first step, we're going to need the molar mass, then we need the coefficients, and then we need gas laws. All right, so let's take our first step here and use this molar mass, 84.01 grams per mole, to get from grams of sodium bicarbonate to moles. Then we can use the molar ratio. There's 1-to-1 moles of carbon dioxide to moles of sodium bicarbonate. And that comes out to be 0.0351 moles of carbon dioxide. So that is N, our number of moles of gas. Now we want the volume of gas, so we can use the gas law, PV equals nRT, and that rearranges to that the volume is nRT over P. So N is our 0.0351 moles. P is in atmospheres, it's 1.024 atmospheres. So we're going to use the value of R that is based on atmospheres, the 0.08206 liters atmospheres per mole Kelvin. Unfortunately, I'm running out of room on the screen here, but 20.6 degrees Celsius is the same as 293.8 Kelvin. So that also needs to be in the numerator over here. And when we solve for that, that comes out to be 0.826 liters of carbon dioxide gas. So if the conditions are STP, then 1 mole is 22.4 liters. So our 0.0351 moles of gas, that would end up being 0.787 liters of CO2 gas. So the first problem is a little bit larger volume because we're not at that cold temperature of 0 degrees Celsius. We're at 20.6 degrees Celsius, so it's going to have a larger volume in that case. So it's slightly larger than if we were at STP. So these are the two different ways that you can use to convert between moles and volume of gas, depending on whether you're at STP or other conditions. So let's try this next problem. This time we are starting with liters of gas. We have the amount of chlorine gas in liters. So we can use gas laws to convert that to moles of chlorine gas. And then we want to know how many grams of aluminum chloride we can produce. So we're going to have to convert this to moles of aluminum chloride first, and then we can convert that to grams of aluminum chloride using the molar mass. And the molar mass is 133.33 grams per mole. We are not at STP, so for this first step, getting from liters, which is volume, to moles, which is N, we're going to use the ideal gas law. We're trying to solve for the moles for the N, so PV over RT equals N. And the pressure we have is 776 millimeters of mercury. The volume is 5.86 liters. The R that we're going to use is the one that uses millimeters of mercury, so that's that 62.36 liters times millimeters of mercury per mole Kelvin. And then the temperature is 298.7 Kelvin. When we convert 25.5 degrees Celsius, we get 298.7 Kelvin. So the millimeters of mercury will cancel, and the liters will cancel, and the kelvins will cancel, and we'll be left with moles in the numerator. And that is 0.244 moles of chlorine gas. So now that we have moles of chlorine, we want to get moles of aluminum chloride. We can use our coefficients here, that 3 moles of chlorine make 2 moles of aluminum chloride. And then the molar mass of 133.33 grams of aluminum chloride per mole of aluminum chloride will then give us 21.7 grams of aluminum chloride. So for the next couple of problems, your textbook provides a few formulas where you can solve for the molar mass of a gas. If you wanted to, you could just use the ideal gas law to solve for moles and then put that in as grams per mole and do it in 2 steps, but they've just kind of provided you here what would happen if you wanted to get to the molar mass directly. They kind of derived the formula that if you want the molar mass directly, you can put the mass of the gas into this equation and you would end up with grams per mole. So let's go ahead and take a look at how that works. The volume of the gas that we have is 275 milliliters. Since our value for R is in liters, I'll go ahead and convert that to liters. Our pressure is 1.008 atmospheres, so I can go ahead and just use the R that is based on atmospheres, the 0.08206 liters atmospheres per mole Kelvin. And then the temperature is 21.2 degrees Celsius, which is 294.4 Kelvin. So again, if you wanted to do this in 2 steps, you could use these pieces of information to find out what N is using the ideal gas law, and then take the mass and divide it by that number of moles to get the molar mass. But you could also plug it into the formula directly. The formula that the molar mass is the mass of the gas times RT over PV. So we have the mass being 0.185 grams. For R, we're going to use 0.08206 liters atmospheres per mole Kelvin. For the temperature, we have 294.4 Kelvin. And for the pressure, we have 1.008 atmospheres. And for our volume, we have 0.275 liters. So the atmospheres are going to cancel, the liters are going to cancel, the kelvins are going to cancel, and we're going to be left with grams per mole, which is the molar mass. And this ends up being 16.1 grams per mole. So again, if you have the molar mass that you're trying to solve for, you could figure out the number of moles that are in your sample and figure out the molar mass that way. Or you can plug it into this equation that the density is mass over volume. So if you replace mass over volume with density, then the density times R times T over P would also give you the molar mass. So let's illustrate this with an example. The density of the gas is 1.819 grams per liter. Our temperature is 295.0 Kelvin, and our pressure is 0.9986 atmospheres. And let's also write the value for R that we plan to use. Since the pressure is in atmospheres, we're going to use that 0.08206 liters atmospheres per mole Kelvin. So here we have our density, 1.819 grams per liter. We have R, 0.08206 liters atmospheres per mole Kelvin, 295.0 Kelvin, and 0.9986 atmospheres. So our liters are going to cancel, and our atmospheres are going to cancel, and Kelvin are going to cancel, and we will end up with grams per mole for our molar mass. And that ends up being 44.10 grams per mole for that particular gas. Let's take a look at Dalton's law of partial pressures. And that is something that says that the total pressure of a collection of gases is equal to all of the pressures, the partial pressures of each gas added together. So let's do a couple of the easier problems with that. The total pressure in this tank is going to be the sum of all the partial pressures that are in the tank. So the pressure of the oxygen and the pressure of the nitrogen and the pressure of the argon added together. And when we add all these together, we get 1.077 atmosphere. And just remember that since this is addition, we go by place value, and so we added up these values that had 3 significant digits and ended up with something with 4 significant digits because we're going 3 past the decimal. A lot of times, including in one of our lab experiments, we have the total pressure and we have the pressure of one of the gases. We have the atmospheric pressure, and we know what the vapor pressure of water is at that particular room temperature. And we are trying to get the pressure of the other gas. So we take the total pressure and we subtract the partial pressure that we know, and we can get the partial pressure that we don't know. The only problem here is that the atmospheric pressure is given in atmospheres, and the vapor pressure of water is given in millimeters of mercury. So we need to pick one of these units and convert them both to the same unit so that we can do some subtraction. We can't subtract one unit from another. Let's take the vapor pressure of water and convert it to atmospheres. That gives us 0.0272 atmospheres. So we can subtract 0.0272 atmospheres from the 1.042 atmospheres, and that would give us 1.015 atmospheres as the pressure of hydrogen. If instead you had converted the atmospheric pressure to millimeters of mercury, you would have found that it is 771.2 millimeters of mercury. So either one of these answers is true. It just depends what units the question is asking for. This one didn't specify. All right, so let's revisit problem 9.3.6 above, where we figured out that the total pressure in the tank was 1.077 atmospheres because of these three partial pressures. The fraction of the pressure that's in your tank due to a certain gas is the same as the fraction of the moles that are in your tank over the total moles in the tank. So for example, if you had a tank and half of it was a certain gas, then half of the pressure of that tank would be due to that gas. If 0.25 or 1/4 of the tank was a certain gas, then 0.25 times the total pressure would be the pressure of that gas. So let's figure out the mole fractions of these different components. The mole fraction of oxygen is the pressure of oxygen, the 0.430 atmosphere over the total pressure, which is 0.399. It's 39.9%, but we'll just keep it as a fraction instead of a percent. Similarly, the fraction of nitrogen comes out to be 0.505, and the pressure of argon comes out to be 0.0956. And these add up to 1, just like if they were percents, they would add up to 100%. So if we want to know the moles of oxygen that are in the tank, let's go ahead and take a look at this part of the equation over here. The moles of oxygen that are in the tank over the total moles in the tank is equal to the mole fraction, so the fraction of oxygen. So if you want to find out the moles of oxygen, we would take the fraction of oxygen and multiply it times the total moles. So the moles of oxygen are the fraction of oxygen times the total moles, and that is 0.399. And now we just need to find the total number of moles in the tank. We're not told that directly, we're just given the volume and the temperature. So let's go ahead and use some ideal gas law to figure that out. The moles of a gas are the pressure times the volume over the R times the temperature. Our total moles, we're going to figure out the total moles using the total pressure. So 1.077 atmospheres total in the tank. And the tank is 11.4 liters. We're going to use the R value with liters, atmospheres per mole Kelvin. And then the temperature is 285 Kelvin. So the total amount of gas in the tank is 0.525 moles. Let's go ahead and put that here. So 0.399 or 39.9% of that total moles is our moles of oxygen, which is 0.209 moles of oxygen. We can do the same thing with nitrogen. So we have 0.265 moles of nitrogen. And then our moles of argon would be 0.050 moles of argon. So because of some uncertainties in the last digit, these don't actually add up to 0.525, they add up to 0.524, but that's okay. We just have a little bit of uncertainty 3 past the decimal.